Hello and welcome to Beam Call number 4. Today we have an exciting topic, the exit queue. This is the very first call that is unscheduled. So it's a topic that came up a little bit last minute. It's a little bit of a niche topic, but should be a fun call. And today we should be sticking to the 1 hour schedule. So I'm going to start off with a quick round of updates before sharing the floor with to Mike and Malesh. Okay. So first, a few social updates. The first one is that I've added a little bit more information to the 2025 tentative schedule. So in the schedule, we basically have two main parts. The first part is the research updates in the first half of 2025, Q1 and Q2. And the culmination of this is Beam Day on June 29th. We now have dates for the next few calls, APS with Julian and 3SF with Roberto, Francesco, and Luca. And tentatively, we have May 30th as Beam Call number 7 for rainbow staking. And then the second half of, and in terms of choosing the dates, we did the first call on Valentine's Day, and today is Good Friday. So happy Good Friday to everyone who celebrates. The second part of the year will be dedicated to speccing. And here the strategy is to start with subspecs for specific modules and then to think about the full holistic spec towards the end of the year. And in November, we're going to have a Beam Day in Buenos Aires during DevConnect. And maybe, this is half a joke, we could have the final Beam Call of the year on December 26th as a Boxing Day present. Another update that I wanted to share is that we now have Luma registrations for Beam Day. So spaces are limited. We have about 60 spots, and we'll give precedence to researchers and devs. But even if you're not a researcher and a dev, feel free to apply if you happen to be in Cannes 1 day before EthCC starts. And here's a few useful links. The Ethereum protocol calendar, where all of the calls are scheduled, the ETH consensus dev on Discord, as well as the playlist on YouTube where all of the calls go. And there's also this very handy website, beamroadmap.org, that O from the Ream team built. Thank you, O. And the final shill that I wanted to give is that we have a new set of calls, the ETH-proof calls, with ETH-proof call number 1 happening on April 25th at 2 p.m. UTC. And it should be a really exciting call with lots of alpha leaked on this initial call, including 3 ZKVM reveals. So those are 3 ZKVMs that have never been revealed publicly and will be first revealed during call number 1. And there's also a Telegram group if you'd like to join the community Telegram group. Okay, on to the meat of today's call, the exit queue. So we have 2 speakers, Malesh and Mike. And Malesh and Mike have been working on this for several months now. So in June 2024, they published an academic paper. And then they published an EIP very recently in March 2025. And even more recently, in April this month, they published an ETH research post to give a little bit of more context on the EIP. And one of the reasons why I'm excited about this research is that it's a combination of 2 beam chain principles. The first one being that we're striving to have a system which is maximally simple, and we're also striving to have designs which are optimal or close to optimal so that there isn't a need to go change them in the future. So with that context, I will share the floor with Mike and Malesh.
Mike, do you want to go first, or just opening remarks, or should I go? And which of us are we going to share, because we have a common set of slides?
Yeah, why don't you show the slides while you present,
Okay.
and then I'll go. So yeah, just as a quick word to kick us off. Thanks, Justin. Yeah, we think the XQ is a pretty important topic, and I guess it's something that we saw gain a lot of attention recently. I think especially when people started talking about staked ETH ETFs, and like obviously we don't want to build a system that is like designed to be a financial product or anything like that. But it just kind of called into question, and it made people think about like, oh, what can like a long execute actually mean, and like how does this impact people interacting with the chain? So yeah, I guess it's Good Friday, so kind of as Justin alluded to in one of the earlier notes, we're kind of trying to revive the exit queue, raise it from the dead. I guess that won't happen until Easter Sunday, but yeah, very very happy to be here. I guess as a word of kind of order, Malesh is going to give kind of a quick rundown on the academic results side of it, and then I'll talk about the practical implications and how we're hoping to apply those. So yeah, all yours, Malesh.
Awesome. This is what you get when you let an economist near protocol consensus. So, apologies if you don't like it, but Mike has tried to make sure that I'm saying sensible things. So the plan, like Mike said, is I'll give you a bunch of theoretical background, and I'll keep it short. And then Mike will tell you practically what that means for our proposal, or at least what our current proposal is. We'll start from where Ethereum is right now and update to that. Please feel free to jump in with questions. There's no need to wait to the end. And also, like, yeah, if you don't ask questions, I just keep going faster and faster until we finish immediately. So I believe everyone can just unmute themselves. I won't be monitoring the chat. Mike, if there is something in the chat, just let me know. Okay. So the Ethereum exit queue and a lot of other exit queues are rate limited. We have discussions in the paper of different queues, but in particular, Ethereum is very rate limited. And a question you might ask is why? So there's some parts of it that are just around sort of, stability of the validator set so that you don't have to keep updating who's in and who's out. But a more sort of economically founded reason is from this definition of Joachim New, Emeritus, and David Say. And they defined accountable safety. So accountable safety is basically the idea that if something goes wrong, so if there's some inconsistency in the protocol, some people aren't agreeing, you can identify a fraction of the validators as having provably violated the protocol. And why do you care about accountable safety? Well, accountable safety is the foundation of the idea that we're using this proof of stake for economic security. That is the idea that if somebody is if something's gone wrong, then you know who's done something wrong. You can punish them. Because you can punish them ex ante, you know that the fact that everybody has voted on something has some underlying economic meaning. Now, the core tension with this is that the consensus models and the simplest definitions of economic security start from a static validator set. So if you start from a static validator set, that's fine. You can make statements about how much economic security is backing a particular transaction or a particular piece of finality. But of course, real world blockchains, people enter and exit. You're not going to commit your stake in perpetuity. And when you allow for entry and exit, what that means is that the accountable safety of a transaction can only decrease over time. So something gets finalized, but once that gets finalized, some of the stake that finalized it might have left the protocol, right? And what could happen is, of course, that the violation might occur, and the stake might exit before you can detect it at the protocol level, in which case you can't hold it accountable. So that's sort of why we...
Oh, Malesh, can I add one thing quickly?
Yes, please. Of course.
Yeah, so I guess one thing I really want to double down on is the fact that the accountable safety, or kind of the economic finality, or the economic weight behind a finalization guarantee, does actually go down over time, right? Like, this is kind of weird because you think, oh, time is passing, like my transaction is getting more and more fork choice weight, which it is. But the reality is, because the validators are able to exit the protocol, the economic security of the finality guarantee itself goes down. Now, of course, the rate at which it goes down, and this is kind of what we'll get to, is very, very slow. Like, the fork choice, the probability of the block getting reorged out, kind of from a fork choice perspective, is going down, but the economic security is going down as well. So I think those two things can both be true, and it's kind of counterintuitive when people are thinking about these systems.
Thanks. Yeah, what he said. All right. So what are we doing? So one way to think about it is we can model the accountable safety requirements that the protocol wants as a collection of validator set consistency constraints. So you could say something like, in time period T1, I only want delta 1 fraction of the stake to be able to leave. In time period T2, I only want delta 2 fraction of the stake to be able to leave, and so on and so forth. So for example, you might say no more than 10% of the stake can exit within 7 days. No more than 2% of the stake can exit within half a day. Whatever those accountable safety parameters that you want associated with the protocol are, you can just write those down as a collection of constraints that you want the protocol to satisfy. And now we need to write down sort of what is the, like, going back to Justin's point about simplicity and optimality. So we've told you something about what we want to do. And now let's think about what is the optimal thing you could do. To define optimality, you need to define some kind of objective function. So here's a particular model in which we can write down an objective function. So time is discrete, and it represents when withdrawals can be processed. So for example, in Ethereum, it's every epoch boundary, every 6 minutes. In Solana, it's every 2 days, whatever it is. And each agent has a cost of waiting. So if you're starting to try and exit and you have to sit and wait for a bunch of time, you're going to pay a cost, this utility cost associated with how much time it takes you to exit. I'll call the cost of an agent ICI, and I'll put down a disutility that they suffer if they have to wait delta I units of time. And what I want to do is I want to write down a protocol that maximizes utility, or equivalently minimizes the expected disutility of people. So I want to I want to minimize the amount people have to pay in terms of the disutility cost of waiting. And of course, I can't do this completely willy-nilly. I have to continue to satisfy the protocol constraints, the accountable security constraints that we specified on the previous slide, right? So under that, let's define a simple procedure. What is that simple procedure? That's the procedure that's going to be the basis of the first part of what we propose, which is what we call min-slack. So the min-slack procedure just says, at each period, look backward in time and greedily process as many withdrawals as possible given the constraint. So look backwards, see how much, based on past withdrawals, whatever that is, the history, see how much of the withdrawal capacity, given the accountable safety constraints you've used up, and then just process as many people as you can so as not to violate any of the constraints. So let's do this by a simple example. To make the example even simpler, let's suppose the accountable safety constraints are given in terms of absolute numbers. So 3 units of stake can leave in the last 4 periods, 5 units of stake can leave in the last 10 periods, and 15 units of stake can leave in the last 20 periods. And here's a simple visualization. We are at time t today. And of course, because the constraints tell us that we have to look back up to 20 periods, you need to know what happened in the last 20 periods. So in the last 20 periods, you had a whole bunch of departures. So on, let's say 17 periods before today, 1 unit of stake left, 15 periods before today, 1 unit of stake left, 13 periods, and so on. So this is the history of previous departures. Okay. And now you're faced with these constraints. There's somebody or a bunch of people who potentially want to leave today in period T. So what do? Well, first you look back to 3 periods before, and you see, look, only 1 unit of stake has left in the previous 4 periods. That was 3 periods ago. So with respect to that constraint, you can process up to 2 more units of stake and still be satisfying that accountable security constraint. So there's a slack of 2. Similarly, you now look back 10 periods. If you count that up and hope that we did it correctly, Mike did it, so it was done correctly. There were 4 exits in those periods. And because there were 4 exits, there's 1 unit of slack. And there were 9 exits over the past 20 periods. So there are 6 units of slack with respect to this constraint. So minimum across all these 3 constraints, there's 1 unit of slack, so you can process 1. That's min slack. So you just count up look at all the constraints, take the minimum that you have, and let that amount out. That means, so given this history, you can process 1 withdrawal. If you had a different history, you'd have a different number. It could be 0, it could be much larger. In the paper, we prove a simple theorem, which is min slack is optimal under common values. So if you think of all validators as having a common disutility from waiting, then the best thing you can do is min slack. That is the provably optimal thing under the assumption that me and Justin have the same sort of impatience to get things done. Now, the reason why it's not optimal in general is that, or why you might not be happy with that sort of assumption, is that people might have extremely different time preferences. So I might be a large validator who also happens to have aped a bunch of money into an Aave borrow position. And that Aave borrow position is getting borderline. So I quickly need to get my ETH out to top up that borrow position and not get liquidated. On the other hand, Mike is just a very sensible, careful validator who is just thinking, okay, it's coming up to that time of month where I need to rotate my key, or time of year where I need to rotate my keys. Mike and I, in that circumstance, have very different time preferences. I need to go immediately in order to not get validated. Mike is like, any time in the next month, it's not a big deal for me, right? So with these heterogeneous values, min slack is no longer optimal. Why is it no longer optimal? Firstly, of course, within any given period, you no longer, even when you're looking at delays, even suppose you have like 2 units of stake that you can let out in a period, you don't respect priority. That is to say, you don't say, okay, Aave guy, you can go first. And the second part is that you might say, okay, I have only 1 unit of slack left, like in the previous example. So you might let somebody who's just rotating their keys out. That means you're now down to 0 units of slack potentially for the next period. And now in the next period, when Aave guy comes along, you have to say, I'm sorry, there's nothing I can do for you. The slack is empty. Wait till the queue opens up. So there are like I said, there are 2 things. 1, we don't respect priority. 2, we don't take into mind that there is a marginal value of holding slack in hand. There is a marginal future option value of holding slack in hand, which is the ability to treat or ability to exit people who have a very high disutility of waiting. So,
Milesh,
of course,
can I ask a question from the chat?
Yes.
So yeah, there's kind of an interesting conversation happening where I guess the way in our model that we represent this heterogeneity is with the different cost, CIs, right? So Vitalik also kind of asked the question of what if cost is not linear in time, right? So instead of the negative CI delta I, what if it's like exponential in time, or there's kind of like a constant fixed cost plus some exponential component? I was just curious if, like from your kind of economics background, if any other model of disutility would make sense, or like, I guess just curious your intuition here.
I don't have immediate intuition. Like if we think that there's a class of utility functions that better models the disutility, we can think about what is the optimal unqueuing procedure for that.
Yeah,
Yeah.
I guess my intuition is that as long as the disutility is kind of monotone in time, like
Yeah.
it still feels like a solvable problem. I think min slack still works um, under any utility function if all the CIs are the same. So that's kind of what we mean by the heterogeneity. Like we're saying CIs are different, so people have these different kind of slopes for their disutility lines. If everyone has the same slope, obviously min slack works. If everyone has the same parameterization of the other utility function, I think min slack is also probably optimal.
Okay.
But yeah, I think it's kind of like a good question and maybe something we can explore later.
I mean, okay, I'm just scrolling through the chat. So, I'll defend. I won't defend it to the bone or anything, but I will defend the linearity assumption a little bit in the sense that there is always an option for me to like in terms of what I can do with my ETH up to. Sorry, there is always like an outside option for me to get my ETH, right? I can borrow the ETH somehow from some other lending market, and that could be a source like so. Because I can borrow the ETH, the interest on my ETH is somehow my disutility of not getting the ETH out of the queue immediately. And my access to, or my access or my ability to borrow the ETH, or the interest rate that I can get for ETH could be my disutility of waiting for the ETH from the exit queue. So that would be sort of on the margin, maybe one reason why you might think it is heterogeneous because it's different people might have different abilities to access a lending market for the ETH, but linear because it's that's sort of the interest or carry cost. I don't know if you buy that, but that would be a okay. You don't buy it. Uh, I guess
We
the question.
we can also take it offline too.
Yeah, we can take it offline. I'm very happy to chat about what you think the right utility model is because we can do it. I mean, we can talk about it. Uh, uh, where to? I'll take that offline. Okay. Yeah, I guess this is the model. I'm quite happy to work through other models of disutility if there's something that's more palatable. All right, where were we? Okay, with heterogeneous values, min slack is no longer optimal because it doesn't do the right trade-off, so it doesn't respect um, the it doesn't respect the sort of differences or the heterogeneity within period, and it doesn't capture the option value of holding on to exit capacity for future periods. Of course, given a distribution, you can solve it out using a Markov decision. It's just a dynamic optimization problem. If you buy, it's just a dynamic program if you buy a particular distribution. But so we sort of model out a couple of things. The Markov decision problem is super messy, so we do a priority queue instead. So that we call prio-min slack. And you can simulate it out for different distributions, and you can compare the performance between the optimal prio-min slack, which keeps into account the option value of waiting, and what it gives you in terms of the disutility. Of course, garbage in, garbage out. If you didn't like the linear utility assumption, you're really not going to you're really not going to like the distributional assumptions in optimal prio-min slack. So, but we show numerically that prio-min slack performs very well. So you could write down a version and does that, and I'll let Mike take over and deal with the questions.
Thanks. Yeah. If you stop sharing, then I'll share mine just
Oh,
so I have
right.
control
Good
over
idea.
the slides. Cool. Here we go. Cool. You should all be able to see my screen, hopefully. Yeah, just holler if anything looks wrong, and yeah, happy to take questions online or after at the end. So, right, that's kind of like setting the stage of what the paper actually said. Now, of course, as Vitalik was alluding to, like some things might not be like part of the model you can take issue with. So I think it's also worth just discussing how the Ethereum withdrawal setup is is constructed today, and then we'll conclude by talking about kind of some of our design recommendations for what Beamchain could consider to kind of avoid some of the mistakes that Ethereum potentially made. Not mistakes, but the design decisions that Ethereum made. Cool. So right, this is the diagram like I kind of have been using to think about the withdrawal flow because it's quite complicated. So I guess there's 4 different timestamps that we'll pay attention to. The first is when the validator initiates a validator exit. So there's currently just one way to do that. You use your BLS key, which is your kind of consensus key. You send a message over the consensus network, and that like voluntary request says, hey, I would like to exit the validator set. At that point, you get assigned an exit epoch and a withdrawable epoch. The exit epoch is the point at which you can stop validating, right? So up until this point, we say the validator is active because they're still expected to participate in consensus. If they don't participate in consensus, then they kind of don't earn any additional rewards that they would have for being online during that time. The next timestamp is the withdrawable epoch. So that's at the point where the stake is kind of ready to be pulled from the consensus mechanism itself. And at this point, the kind of between the exit epoch and the withdrawable epoch, the validator is not active, but they do remain slashable. And the important thing here is that we want there to be some gap between these two so that if they commit a slashing violation right at the end of the active period, so like right at the end of this green period, we have like some amount of time to detect that slashability before their stake is withdrawable. And then the last part is when the withdrawal is processed itself. So the first gap is determined by the exit queue. So that's kind of like what we've been talking about this whole time. In Ethereum, it's this rate limited first in, first out queue. It's just very standard. The way that the rate limit is decided is you take the total number of validators and you divide it by 2 to the power of 16. Currently, that leaves us at 16 validators per epoch. So that's kind of just how we determine how fast that exit epoch gets hit. Of course, now we have to have this delay between the exit epoch and the withdrawable epoch. As a kind of clear case study for why we need this, consider if the exit queue is empty, right? If no one is in the exit queue, then your exit epoch could be like the very next epoch after you initiate your exit. And so there is kind of this fixed 27-hour delay to say, we're going to give ourselves ample time to detect any slashable violation of the protocol. And then the stake will no longer be slashable and will be processed for withdrawal. The last piece is the sweep. The sweep is variable length because it just goes by validator index in kind of a round robin fashion. So you start at validator index 1 and you iterate through all of the validators. Currently, we're at like right over 1 million, I believe. And during each block, you can only process 16 withdrawals. Now, this seems like a lot. You're like, oh, you can only do 16 validators per epoch, 16 per slot. Doesn't seem that crazy. But the situation is set up such that every single validator has a withdraw in this queue processed. And that's because currently partial withdrawals, which are kind of any marginal ETH you earn above the 32 ETH that the principal that you staked, gets withdrawn automatically for you so that you don't have to kind of pay any attention to it. So right now, basically, all of these like I think it's like 0.05 increments get swept off kind of repeatedly, and that fills up the withdrawals for each slot. So that's currently like a bit of a inefficiency in the design, and that's kind of one of the things we'll propose, certainly for a candidate for removing from Ethereum, but also as we can consider like the optimal design for an exit process, like it probably wouldn't have this sweep in there because 9.2 days can be quite a long time. Justin's thing just Hearts just floated up. I don't know what that happened.
I clicked the wrong button. It was react with animation.
Cool. Right. So before jumping into kind of our proposal, I guess, yeah, what I just described was Ethereum as of the last hard fork, which is the Deneb Cancun hard fork. I think it's also worth talking briefly about what changes in Prague Electra. So Prague Electra is scheduled for May 7th, I believe. So coming up a year. And there are some changes, but the kind of core essence of the execute does not change too much. And that's kind of very important to consider. So there's an EIP 7251, increase the max effective balance. Yeah, and there's kind of three features about that EIP specifically to do with the execute that I'd like to highlight. Okay, that went away. Right. So first and foremost, the execute is now denominated in ETH instead of number of validators, right? So on the previous slide, I said you can only process 16 validators per epoch. That only makes sense if all the validators have the same amount of stake. MaxEB changes that so that there can be many, many different validator sizes. So one validator could have 32 ETH, one could have 2048 ETH. And so you can't denominate the execute in just number of validators because they could have very different weights. So you have to say, I want some amount of ETH to be able to exit per epoch, for example. Secondly, validators can choose to compound their stake. And this allows them to trigger partials withdrawals from their withdrawal address. So this is like some jargon. So let me try and unpack it. There's two keys that are involved, or kind of two identities that are involved with the validator. First, you have the consensus layer identity, which is this BLS key. This is how you sign your attestations. This is how you sign your blocks when you're proposing them. This is like a very important set of keys. But separately, you have a place that, like an address on the execution layer where the withdrawal actually gets sent to, right? So you have to like have that ETH accessible somehow within the execution layer. And the way we do that is there's a place you specify what the destination of the withdrawal should be. So if you opt into compounding rewards, basically now you're saying, okay, beyond the 32 ETH, I want all the staking rewards that I get to be redeployed into the validator and keep kind of increasing my relative weight in the validator set. Now, if you recall, the last stage of the withdrawal flow was this partial withdrawal sweep that kind of goes around in this round robin fashion. So by switching to these compounding things and saying, I actually want to trigger my own partial withdrawals manually, like maybe once every month, once a year, whatever, you're opting out of that sweep. So now every 10 days, instead of every single person processing withdraw, you only process people who haven't switched to this compounding stake credential. So that's kind of an important piece. And then lastly, kind of again, double clicking on this, this withdrawal address, validators can trigger exits from the withdrawal address. So previously, that kind of first step of the pipeline, which is initiating the validator exit, we call these voluntary exits because it's kind of initiated by the validator, not from the protocol itself. And now validators can trigger those from the withdrawal address as well. So not only can you trigger partial withdrawals, but you can trigger full exits. And these two things are kind of important. And again, I'll double click on them when we get to the kind of beam chain recommendation section. Just taking a quick time check. Okay, it's 8:36. Yeah, I think we should be good. So what is our proposal? You know, we've kind of been yapping at you forever now. Give us some details. So what we're proposing is what we call single constraint min slack. So Malesh talked about min slack being you kind of enumerate a list of maybe n constraints. Maybe you have 10 consistency constraints that you want to say about the protocol. And min slack goes through each of those constraints, determines kind of the remaining, the minimum one that has slack available, and consuming all of the slack in that subject to that constraint. But we're actually taking an even simpler approach here and just saying, okay, specify a single constraint that you care about. Normally, like this could be like something like the weak subjectivity period, like over 2 weeks, we only want 5% of the stake to be able to exit, or over 90 days, we only want 25% to be able to exit or something like that, and kind of enshrine that single constraint and then let the protocol do whatever it wants outside of that. So how does that compare to what we have today? So today we have this setup here, which is effectively a constraint per epoch, right? So we're saying in the next epoch, only 16 people can exit. In the next 2 epochs, really only 32 can exit and only 16 in the epoch after the previous one, and so on and so forth. And this new constraint per epoch is like very limiting in what the protocol can do, because now if you have like some variability in demand for exiting, like even if the average is 16 per epoch, you can still have periods of like high congestion because everyone's trying to get out at the same time, and then there's periods where no one's trying to get out. So that's kind of the situation we're trying to avoid for. I guess switching the denominations of these constraints into something that looks more like the min slack constraints, we can say like, oh, currently we only allow 0.0015% of the stake to rotate per epoch, and kind of you can take that out over longer time horizons. So yeah, the kind of thing I was alluding to earlier is that in reality, this is probably too many constraints, right? Like no one is looking at the per epoch granularity and saying, okay, my transaction has 0.034% decay in safety over 1 day. Like that just feels like kind of unnecessary to codify that many constraints. So we propose this kind of single thing that gives everyone the same guarantees and allows the exit process to be much more flexible. So if you haven't seen The Incredibles, you should watch it. It's a great movie. So yeah, there's a line. Elastigirl is very flexible, and her husband, Mr. Incredible, says you need to be more flexible. Right. Shitpost aside, let's continue on. So how does single constraint min slack actually work? We're kind of calling it, or I guess one nice way of thinking about it is this idea of retrospection. So the protocol currently only can look forward in time, right? It doesn't keep any history about the past withdrawals. It just says epoch n, you can withdraw 16, epoch n plus 1, 16, all the way forward carried in time. And in aggregate, over the m plus 1 epochs represented here, no more than 16 times m plus 1 exits can be processed. So what does retrospection mean? Retrospection means instead of that, what if we looked back in time? So we keep some history of the amount of people that have exited during the past 16 times m plus 1 exits, and we use that to enforce the consistency constraint, right? So now we say epoch n is the present epoch. We're looking back m plus 1 epochs to epoch n minus m. And looking back in time, we can say, how many withdrawals have we processed in that time period? Okay, what is our consistency constraint? Given those two numbers, we can calculate the amount of stake that we can withdraw in the current epoch. So that's kind of super simply what this is trying to do. And yeah, that's this retrospection. Yeah, go ahead, Malesh.
No, just like the one sentence TLDR is we're just taking some given constraint seriously. For example, no more than 10% of stake can leave in a month, and just maintaining that invariant. So we're always looking back in time a month, and we're saying how much is left. The amount you can take out is whatever will not get you past this 10% invariant. It's a one invariant system. The actual proposal is slightly more complicated because we're trying to be nice about, or trying to be a little more sophisticated about a few things. But the idea is just you pick your invariant, tell me what you're happy with, and then we'll just run with that invariant. Thanks.
Yeah, and I guess it's also worth pointing out that with this invariant, you have kind of the guarantee that over every 2-week window, or every 2-week rolling window, that consistency is there. So you kind of have this kind of every epoch you move forward, you take the epoch 2 weeks ago and you toss out the exits that were in that one, and you only consider the kind of intermediate ones as part of your consistency constraint. Right. So I included a few spec highlights just, to show that it's actually not too difficult to implement this. I guess there is, right. I'll add some caveats at the end, but basically we use a few different things. First, we use this exit churn vector. The reason we do this is to simplify the accounting, right? So right now, if we counted the exact number of exits that were processed in each epoch, that's kind of a lot of data, right? Like every 6.8 minutes is an epoch, and you'd have to write a new piece of state, like consensus layer state data down for all of that. So we use these generations to simplify things. We say a generation is about 27 hours, epochs per generation. And we kind of account for 16 generations in our history. So that's the only thing we have to add to the state is instead of this kind of running tally from each epoch, we just keep the running tally from the past 16 generations. And then the actual kind of like meat and potatoes of min/slack is codified in this for loop. We basically say how much churn did we use, and let's like given how much we have left over the past 16 generations, how much can we consume in this generation? And that's kind of all that's happening here. There is some tech debt here, and I call it tech debt because if we were building this from scratch, I don't think we would have this issue, but because of the way that Ethereum exits work today, we have to explicitly set this exit epoch kind of when you first hear about the withdrawal, not when you actually process it, right? So there's kind of different ways you could think about designing this if you started from scratch, but because we have to do this, we have to like look forward and map the exit to a specific generation in the future. So we're like looking a few generations in the past, 2 generations in the future, mapping the current exit into some generation into the future. And that's how we explicitly set the exit epoch, like when in the initial stage of the processing of the withdrawal. A more natural approach, I think, is to maintain kind of, and I guess this is definitely like for the engineers to answer, not for me, but intuitively, what's a more natural way to do it is to maintain some sort of state that says these are all of the exits that are pending, and only when we process them do we have to set the exit epoch. And then you can kind of do this thing where we only look to the past and we only use this retrospection. But yeah, that's kind of how we implemented it, at least in the EIP. I think this is all very subject to debate, and like if people want to go back and forth on the spec, that's probably very useful. I guess yeah, I'll leave it there. Right. So I want to highlight. I have like a few minutes more that I want to highlight a few proposals, and then we should have like maybe 10 minutes for Q&A. So as you might have detected in my kind of earlier discussion, I think we should also consider getting rid of the partial withdrawal sweep, just because that extra 9.2 day delay, I guess on average it's 4.6 days, but seems very inefficient to have that mixed in with the full withdrawals. So either you can remove the partial withdrawal sweep altogether, or you separate partial withdrawals and full withdrawals into like separate lanes, and you don't bottleneck them in the same process. So this right out of the gate, this could save on average 4.6 days per exit. Also, there's this priority fee ordering for withdrawals that kind of could be considered. So up until this point, I guess Milesh told us that min/slack itself is optimal under this heterogeneity, under homogeneity. If there's different priorities for exiting, then implementing prio min/slack is a clear improvement. And one way you can implement this is by allowing people to kind of explicitly bid or explicitly kind of tell the protocol, this is how much I'm willing to pay to get out. And then you can, once the protocol has a view into that market, then they can order based on like highest amount that people are willing to pay. And this is kind of like one way you can implement prio min/slack. It's one way you can elicit bids. Obviously, there's some questions around what is the kind of procedure for bidding? What's there's some market design questions, I would say, that go into like, what do you do with the amount that people are willing to pay? Do you burn that ETH? Do you give it to the validator that processes the withdrawal? Like there's kind of questions there, but this is one way you could do that priority queue and elicit information from them to allow you to like handle the withdrawals in a more priority queue way than a first in, first out. Right, as we kind of alluded to earlier. Okay, cool. So just gonna highlight 5 or so beam chain suggestions, and then we'll open up the floor for Q&A. So first, definitely denominate in ETH. I think this is a no-brainer. If your validators are going to have different stake weights, then you have to denominate the exit queue itself in that numeraire. Don't do the sweep. I think in general, yeah, the partial withdrawal mechanism was kind of built for a world where I guess I'm actually interested now in the history. Maybe Justin or Vital can share, but the partial withdrawals logic, that happened before full withdrawals were even enabled, or did they happen at the same time? I think it actually happened at the same time, which is in the fork after the merge. which is the Capella hard fork. But anyway, the point being, this is a world where we were building proof of stake kind of like in two parts, I guess. The first part was, well, in many parts. The first part was the beacon chain, and then the actual merge itself, and then the withdrawals weren't enabled until after the hard fork, after the merge. So I guess I'm not saying that like any of the decisions we made in the past were wrong, but I think kind of starting from scratch, it's pretty clear that the sweep should not be part of the design. We suggest single constraint min slack, probably the right place to start, at least in terms of like only defining one constraint and one invariant that you want honored by the process. Also, this pay for priority thing is certainly interesting, and it ties in nicely to this next question, which is, I think it's important to get right how the integration with the execution layer works. So I think this is another thing that that in Prague and Electra we're kind of paying a lot of attention to, which is how, like, what set of validator controls are accessible from the execution layer itself. So from a smart contract or from a key, from an EOA that is like controlling the validator itself. And I think this is probably the correct way to implement this pay for priority thing. Like you'd have maybe an auction where you sell the right to exit 5 slots in the future, and you conduct that auction with like a native contract on the execution layer, and then that data gets consumed by the consensus layer. So I think that's probably the right way to do it. Again, the exact CL-EL interplay and how that will work out in Beam Chain, I guess, is still probably up for debate, but that's at least on surface what I would suggest for y'all. So yeah, thanks very much. This concludes our presentation. We have exactly 10 minutes left in the hour. So yeah, here's just the links that we've kind of been discussing and sharing over the course of the call, and super happy to take questions, and thanks again for having us.
Ooh, thank you, Mike and Malesh. This was a great presentation. Please raise your hand for questions. Terence.
Yeah, this is a great presentation. Thank you. Have you thought about running this algorithm on current mainnet and just backtrack all the data over the last few years and just see like how much improvement, I guess, in terms of utility? I'm curious what that would look like.
Super interesting.
So
I guess, yeah, you want to answer, Balash, and I'll
yeah, I
follow
can
up?
answer that. So like at least we looked at, okay, we've ran this visually. What does that mean? We looked at the historical validator exit queue, and if you look at it, there's only one period where the exit queue got past a day. Okay, so you look back at like validatorq.com, it's never happened. I think the bigger concern is not that it has never happened. The concern for a lot of people, and Justin said there were people from Lido who would be in this call. There are lots of other institutional stakers. For them, the concern is not that it hasn't happened. It's what do we do if it does happen and we have like 5% of stake waiting to get out, just like we've seen. I guess maybe a different answer to your question is we could rerun it on Holesky or something and see what that would do for us, where there is like a massive queue waiting. But on mainnet, we've never had a massive queue.
Yeah. So I do think it's interesting. I'll say that we wrote this paper very much as like a theory paper, not an empirical paper. So we didn't go through and like process all the withdrawals. I do think it's an interesting question. I guess some institutional staking people asked me kind of like on average, how long has the delay been? And the best data for this, I think, is the validatorq.com. So that's where I'd point you. I also wanted to call out, Vasily had a nice comment that is the average attester slashing is about half an hour. And that's something I didn't mention in the talk itself, but if scrolling back to this, I think everyone agrees that there needs to be a delay between the exit epoch and the withdrawable epoch. That delay being 27 hours or 256 epochs, I think was made in an abundance of caution. Like there wasn't any data on slashing at that point because the proof of stake didn't exist on Ethereum yet. So I think re-examining that number is also something that could be like a candidate for improving efficiency. And yeah, I definitely agree that 27 hours feels very long. I guess under the world of like a network level attack, we're trying to like partition or like eclipse some subset of the validators. It might be important to really be cautious. But yeah, thanks, Vasily.
One question I have is, Malesh, you talked about the exit queue not going over one day, but what about the deposit queue? Presumably similar improvements can happen there.
Yeah. So we are less, I guess, I mean, the entry queue, we understood the constraints that we were trying to solve for. The exit queue, like that there's the accountable security constraint. There is an entry queue, and some of it is, I guess, for validator security. Like you can rewrite this for the entry queue. You just have to tell me what is the underlying constraint that is making entries scarce. And once we agree on that, we can, if it's a similar kind of, you don't want more than 10% of stake to enter in a month or whatever, then we can redo the computation. We didn't have an underlying principle that is governing why there is an entry queue. Maybe Mike knows.
Yeah, I think in general, the reason for rate limiting the entries historically has been that the overall set doesn't change too quickly. And there's people in this call that are much more, aware, and like, Vitalik and Justin, like, were there designing it. Right. And Terrence says it's for influence on finality of fork choice. So yeah, I guess in our paper, we restricted our attention to the exit queue because that's the thing that we felt like is like the simplest thing we can capture. I do think it's worth examining the entry queue and thinking about very similar questions. As far as I can tell, it's symmetric, I believe, as presently constructed, which is the same amount of stake can enter as can exit. And obviously that doesn't imply that like the validator set can grow if the entry queue is more full than the exit queue. And I do think there was, I guess, kind of calling back to the second question, which is how have you looked at the data? That was Terrence's question. I think there was a period where the entry queue was very long, right? And that was like immediately after withdrawals were activated, kind of there was this massive rush for everyone to get into the consensus mechanism. And during that period, I think even when I deployed my validator, I think it took me like 2 or 3 weeks before it was actually active. So quite slow. But yeah, definitely worth considering in future work. And I want to answer one other question from the chat from Una Wood. Which of these suggestions absolutely require the beam chain, e.g. min slack, proud min slack, no sweep, all could be beacon hard forks as well without overwhelming difficulty? I definitely agree. That's why we proposed to the EIP to, the Ethereum chain instead of necessarily just to the beam chain. That being said, I think there's pushback, and probably fair pushback, that this is what we're designing in this EIP is an upgrade for the validators, right? And generally speaking, focusing the Ethereum hard forks themselves on kind of like things that are facing more the application layer users and the chain users themselves rather than the validators is probably like where the priority will be. And I think after EIP 7251, which turned out to be like way more complicated and intricate than I think anyone expected, there's probably not going to be a huge core dev appetite to like touch exit queue stuff again. Like it's just like a very kind of painful piece of the process. So I think we'll continue to push some of these EIPs, and like maybe they'll be done by Ethereum mainnet eventually. But I guess it's also useful to just think through the ground up rewrite approach, and that's, I guess, why we're presenting a beam chain as well. So thanks for the question. Oh, there's one more question. Oh, it might have been answered already. Oh, yeah. The meeting is about to end. Oh, that's Fireflies.
One question I have is regarding the generations. My understanding is that you're trying to minimize the amount of bloat in the state. I guess one potential downside here is that it creates this spikiness at the boundaries of generations. And that might be kind of bad for things like snarkification of the chain, where we want to reduce the worst case processing. Yeah. Is that the only reason for having the generations?
That is the only reason. Like it will just, I think we had some of our friends at Teku look over this.
Yeah.
Where Yeah, I mean, Mikhail is on the EIP, and then other engineers, and they were just like, dude, we're already like slammed at epoch boundaries. So please don't do something at every epoch boundary. Like, you could pre-do some like. Anyway, I understand that we're doing an even larger calculation, right, at generation boundaries, but maybe you can smooth that out somehow or amortize that cost. It's just not adding something at every epoch. That was the only reason. It actually makes the proposal, as you can see, harder to grok, so we're not thrilled about it.
Yeah, and I guess this does relate to there's another EIP. Justin and Lynn have an EIP that kind of deterministically sets the schedule for leaders and doesn't allow changes in effective balance to reshuffle the leader selection. And I think there was similar pushback on that EIP, right? Which is if you do these at the epoch boundary, it's like more overhead. And, I guess Francesco and Luca will talk about this in the single slot finality thing, but if you don't have this epoch boundary constraint, like maybe this alleviates a lot of the kind of bottleneck and you can just within a single slot finality world, you don't have to worry about these epoch processing things. So hopefully the tech debt that we saw when we were trying to implement this in Ethereum isn't present.
Yeah. I mean, one of the goals in the Beam chain is to try and reduce the number of arbitrary timeframes that we have and just process everything as much as possible on a slot by slot basis and have it very, very smooth and basically remove the spikes at the boundaries.
Well, there's a long conversation going on. I don't think we'll be able to capture it in the next minute, but yeah, I guess we can continue it in the Beam chain chat potentially, or if anyone wants to reach out, we're super easy to find on Telegram and Twitter and stuff. So please do.
Actually, what I'll maybe do is put the chat in the Telegram group that we have and basically rename it to Exit Queue, Enjoy Yours. And anyone who wants to have a post-call discussion, please DM us and we'll add you to the post-call discussion. Mike and Milesh, thanks again for the great presentations and discussion. And we'll see you all in a couple of weeks for Beam Call number 5. Thank you.
Thanks so much.
Thanks for having us.
Bye.
Thank you, guys.
All right. Thanks.